Assalamualaikum and very good morning. During our lecture today, we will discuss on two more examples of the Fourier transform pairs, which are triangular signal and exponential decay signals. Then we will touch on Fourier transform and Laplace transform. For triangular pulse, the Fourier transform is as shown in the slide, where we have xf equal to v1 over tau times sine pi f tau over 2 over pi f squared. Okay, now we have the triangular pulse signals as shown. Let us find the Fourier transform of this triangular signal. Okay, the solution is referring to Fourier transform equation. We have xf equal integral of function times exponential to the power of minus j 2 pi ft. For this triangular pulse, we have to divide into two. The first one is between negative minus tau over 2 to 0, and then 0 to tau over 2, where the equation for the function for the between minus tau to 0, the xt is 1 plus 2 t over tau, and from 0 to tau over 2, the xt is 1 minus 2 t over tau. When we write down this equation, we have to do integration by parts to solve the Fourier transform for the signal, where we have for the first part, the u is 1 plus 2 t over tau, where du 2 over tau dt, and the second part, the u is 1 minus 2 t over tau, therefore the du is minus 2 over tau. And for both, the integral dv is v equal minus e minus j 2 pi ft over j 2 pi f. Okay, in this slide, I differentiate the uv with red color, and then the integral v du with the black color. And we have two parts, one for signal between minus tau over 2 to 0, and the second one is for 0 to tau over 2. You can look the portion when you see the integral duration here. So we solve one by one. For the second line, we substitute the first one for 0 to minus tau over 2. Okay, so we do the same for the integral of v dv, and then we repeat that for the second half of the signal. So when we do that, we can have the answer. And if you notice, for the second line, the uv can be cancelled out, so leaving us only the integral v du. So in this case, I differentiate for when e equal to 1 for the color purple, and e j pi f tau for color black. So therefore, we only leaving us with only 4 terms. Okay, for both signal from minus tau to 0 and 0 to tau over 2. Finally, we have the equations. So the purple is for e to the power 0, and the black when e to power j pi ft and e to the power minus j pi ft. And we rearrange the equations, so therefore we can have a pattern. So if you look here, this one resemble cos theta. Then we rearrange the equations and replace the square bracket here with cos theta, where we have our theta is pi ft, and then with the equation of sine square, where we have 2 sine square pi over 2, which is from 1 minus cos theta. And if we look at our equations, the third line can be replaced with 2 sinc function. Okay, so finally our xf equal to as shown on the last line of this slide. Before we proceed with the next Fourier transform pair, let us look at the similarities and differences between Fourier transform or ft and a Laplace transform or LT. For example, here, let us find the Fourier transform for the signal below, which is xt equal to exponential to the power at ut, where a more than 0. And then when we find the Fourier transform for the signal, finally we have which is equivalent to 1 over a plus j omega. And if we recall, it is close similarity with Fourier transform, where LT for a similarity with Laplace transform, where LT is Laplace transform. If you can recall, Laplace transform for exponential function, we have 1 over s plus a. And just now, when we do the Fourier transform for the exponential signal, we have 1 over j omega plus a. So in other words, s can be replaced with j omega. As a summary, Laplace transform of fs equal to integral of 0 to infinity ft exponential to the power of minus st dt, whereas for Fourier transform of f, g omega equal integral minus infinity to infinity ft exponential to the power minus j omega t dt. Very similar definitions with two differences. Laplace transform integral is over 0 to infinity, whereas Fourier transform integral is over minus infinity to infinity. Laplace transform, the s can be any complex number in the region of convergence, ROC, and Fourier transform, j omega lies on the imaginary axis. Therefore, if ft equal to 0 for t less than 0, if the imaginary axis lies in the ROC of Laplace transform, then the Fourier transform equal to Laplace transform. If the imaginary axis is not in the ROC of Laplace transform, then Fourier transform doesn't exist, but Laplace transform does. Okay, if ft not equal to 0 for t less than 0, then Fourier and Laplace transform can be very different. Okay, now let us look at the last Fourier transform pair, which is the decay functions. We have two types of decay functions, so let us look the first one. The question is find the Fourier transform of this signal or causal function, they call it x1t, with equal exponential to the power of at ut, where a bigger than 0. The function is an exponential function with a time constant tau equal 1 over a. The Fourier transform is shown in the slide, step-by-step derivations. And finally, we have x1f equal 1 over a plus j2 pi f. And the figure at the right bottom side shows the magnitude versus frequency for this signal. If we look at these two functions, both functions are exponentials with the time constant tau equal 1 over a. They switch between 0 and 1 at t equal to 0. Otherwise, they are absolute integrable, well-balanced functions. One is referred as causal function and the other one is anti-causal function. The Fourier transform are given here for x1, which is 1 over a plus j2 pi f, and x2 equal 1 over a minus j2 pi f, and the functions and their Fourier transform are plotted, and the graph show normalized magnitudes of Fourier transform for x1 and x2. You can have the question as shown in the slide as an exercise for you to do this weekend. So we end today's class. Next class we'll discuss on the Fourier transform properties as well as the Fourier transform pairs. Finally, we'll look some examples on the inverse Fourier transform. Thank you.